Welcome to CS3308 Information Retrieval. This is the Unit 3 lecture part 1. During this lecture, we're going to define and talk a little bit about the space problem. So you might be wondering, well, what exactly is the space problem? The space problem basically boils down to this. As we start talking about and looking at and thinking about creating these inverted indexes, the ability to index very large amounts of information, such as an entire collection of books, or all the content within a library, or perhaps all of the content in the internet. Now, the problem you think about is that content is that's going to have a lot of terms, and we know that in an information retrieval system, we're going to tend to have a lot of terms in our dictionary. So this would be the items that we have in our term dictionary. We know that there's going to be a lot of entries in our posting list, and of course every one of these postings is going to refer back to some file that's in the corpus so that we can identify where that particular term or posting came from. Now, the problem with all of this is that it starts to consume a lot of space. Just to kind of give you an idea, I recently saw a McKinsey report that talked a little bit about the growth, the explosion of growth, and they said that currently the Library of Congress, it has to accommodate somewhere in the neighborhood of 275 terabytes of just textual data. So just the textual words that they have in the books and materials that are digitized, not images or anything else, just the text, it's roughly 275 terabytes. And if you think about it, a terabyte is essentially 1,000 gigabytes. So this is very large. You can get a sense of just what it's going to take to index the Library of Congress. And of course, the Library of Congress and all the data that it contains is absolutely dwarfed by what is on the internet. We also know that corporate data is growing at a phenomenal rate. And in fact, there's an expectation that within the next 3 to 5 years, the amount of data that exists will actually have increased by almost a factor of 50. So we have a space problem. On one hand, we need to be able to index all of this data so that we can find it. We have data in documents, and of course it does us absolutely no good unless we have a way of discovering where it's at and identifying where it's at. And when we start talking about getting into billions and billions of pieces of information in documents or in other forms, we have to have some way of finding it, of searching it to find it. And of course, this creates a bit of a space problem because even the indexes become substantially large. So we have a space problem, and we've got to find ways that we can kind of reduce the amount of space that we're consuming. And one of the strategies that we have around that is to look at various forms of compression. So we're going to kind of begin to start talking about some of these topics around compression, and you're going to see that this concept is continued throughout the entire unit. So why compression? Obviously, we're looking to use less disk space. We know that we're going to require a lot of it. Information is growing rapidly. And the reality is it gets to a point where we simply don't have enough money to build the systems necessary to index all of the data that we have. Secondly, when we think about the index, and we're talking about the dictionary and the postings list and the file dictionaries that we've been talking about as it relates to indexes, we want to try to keep as much stuff in memory as possible. And the reason why is because it allows us to read or to look through those indexes faster. Now, as the indexes become larger, it's going to take longer for us to identify any particular piece of information within it. So it's going to take longer to do searches. And so we've got to do everything we can to make sure that those searches remain very, very high performance. Those of you that have had the opportunity to take the analysis of algorithms course, where we talk a lot about big O and algorithmic complexity and the need to have super efficient algorithms, this is one of these areas where efficiency really does matter. Okay, so again, in terms of getting back to the speed factor, by we want to try to keep as much as we can in memory, but we realize that that's simply not going to happen. Memory is limited. Disk space is going to be larger in one form or another. So we really need to figure out how do we increase the amount of speed that we get as transferring that data from the disk into memory. And one of the ways that we can do that is by compressing the data in some form. And using the power of CPU performance to offset what we may not have in terms of disk performance. And there's a really good principle behind this, by the way. If any of you have heard this idea of Moore's law. And basically, Moore's law came from a guy by the name of Gordon Moore. He was one of the very first CEOs at Intel, and he basically made the prediction that computing power would essentially double every 18 months, and that its cost would go down. And so far, Gordon Moore has been right. CPU power has been increasing dramatically, roughly doubling every 18 months, and the cost keeps dropping. So the cost for every compute cycle is dramatically dropping. In fact, during that 18-month period, it goes down by half. Okay, so I get the same computing power for half as much money again, and so on and so forth. And so essentially what's happened is that we are dramatically increasing our computing capacity. However, there have been moderate gains in the performance of disk drives, but not significant, and certainly not at the rate that we've seen in the computing side of the thing. So what Moore's law basically says is that I know that my computing capability is going up dramatically faster than my disk performance capability. So when I have the ability to trade computing horsepower for disk performance, it's a good thing. And that's essentially what this point down here is making, is the idea that let's assume that what I'm going to expend in trying to decompress data that I may have compressed in an index, well, the decompression is going to be something that's going to take CPU power. It's going to consume CPU cycles. But according to Moore's law, those CPU cycles, I'm going to have more of them at a lower cost than I'm certainly going to have with the disk drive. So it makes more sense to compress the data, try to take advantage of what performance I have in the disk drive, and then improve that in performance by using all of this horsepower that I'm getting cheap, these additional computing cycles, because Moore's law tells me they continue to go up. So why should we be looking at compression for inverted indexes? Well, obviously because we want to reduce the size. We want to make it faster. We want to minimize the amount of effort or the amount of time that we're going to spend using up trying to move stuff from disk into memory. Okay, and we want to try to do all of these things as cost effectively as we possibly can. So when we're kind of thinking about the dictionary, and remember the dictionary of terms, it's essentially that portion of the index where I'm going to have all of my terms, and I'm going to have them sorted in a format that I can go through quickly, maybe with a binary or a B tree type of sort, which we've talked about before. And so our objective there is, if at all possible, to try to make it small enough to keep it into main memory. Now, memory has been going up. Memory has been getting cheaper. So like CPU, okay, we have seen that memory is increasing at a pretty rapid rate. We're definitely certainly not at the rate that we've seen in increases in the CPU performance, but we are getting more dense and cheaper memory. So obviously there's an advantage to trying to find ways to take our dictionary and make them small enough to fit into main memory. Okay. If we make it small enough, we can start to keep some of the posting lists in main memory as well. It's always good. And again, keep in mind that essentially what happens here is that I have, this is my dictionary, has all my terms in some sort of form that I can then find them quickly, and they point to a postings list. And generally, we would potentially even have this in it would be in a totally separate file. And what would be in there is essentially I would have a series of numbers, and then these numbers refer back to the document. So there's kind of a third file out here somewhere that says document 1 is equivalent to my data .text or whatever it happens to be, right? So each one of these numbers refers back to a document. So this is the postings file here. This would be our document dictionary, and of course this is our term dictionary. So really try to keep it small, try to get it in memory if at all possible. In the postings file, what we want to do is to reduce the disk space needed. Obviously, for two reasons. One of them is such that I have more space in which to index data, because again, we just talked about the fact that the data is increasing at a significantly rapid pace. Secondly, I want to reduce the amount of disk amount of storage that I'm going to need to read from the disk and transfer to memory, because again, disk access is relatively slow. I did an analysis for a book that I'm in the process of writing, and it kind of looked at what is the timing between memory and disk, and it was rather telling. But if you think about it, we record or keep track of the speed of memory in terms of a nanosecond, kind of usually abbreviated as NS. And in disk drives, we are using millisecond. Now, there's 1,000 milliseconds in every second. So it's actually a relatively short piece of time, right? Until you kind of compare it with what nanoseconds are. So there are a million nanoseconds in a second. So, when I'm accessing memory and I'm operating at nanosecond speeds, it's extremely fast as compared with the amount of time that it takes to actually access data off from a disk drive. So again, we want to reduce the impact of this performance, this slow performance, and it is relatively slow when we compare it with memory. We want to reduce the impact of that relative performance, and what's one of the reasons why we're looking at compression. Okay, just a couple of words on the idea of lossless versus lossy compression. And the basic idea of lossless, it basically says that, I'm going to compress data in such a way that I guarantee that what I get back is exactly the thing that I started with. And, sometimes that's important, and sometimes it's not. And when I don't absolutely positively have to have every last bit of information, then, I can perhaps do lossy compression. And that basically means I may not have as precise a data when I uncompress it, but generally, depending upon the design, maybe it's good enough. And so this is a decision we have to make. Let me just kind of point out something in terms of lossless and lossy. We have already talked about things that are kind of compression techniques that are lossy, right? So we've talked a little bit about stop words. We've gotten rid of some stuff because it wasn't all that relevant. So it's lossy in that sense. We've also talked a little bit about the idea of stemming, right? So where I would try to cut off the ends of words because all I really find that's relevant is the root. Again, that's a form of compression that is lossy. It's losing some information, but we're saying it's okay that we lose that information. So because of the fact that I don't need it. It's not that relevant. Okay, so a number of these things that we can go on and do there. So another thing that we're going to look at here, and just kind of cover this briefly, is this whole idea about vocabulary and the collection size. And we're going to cover a couple of terms simply because they're relevant and some what they call power laws that help us to calculate and estimate what these things are and what they mean. And the reason why it's important that we have an understanding of some of these power laws is because it helps us to estimate exactly what kind of space we need for our information retrieval system. Perhaps it helps us to estimate whether or not we're going to be able to fit this in memory, since we know how much memory perhaps we have in our particular server. We may also help us to think about how, if I need to, I might be able to divide or split up my index and spread it across multiple different server implementations, as an example, simply because it allows me to fit the pieces into memory. So, what we're going to really focus on in this section is really how big is the term vocabulary, and it basically boils down to how many distinct words do we wind up having in the dictionary. We know that this can be impacted by a couple of things, right? Because when I start using things such as byword indexes, etc., our vocabulary gets dramatically bigger, and that's one of the disadvantages of using those kinds of indexes. So advantage, I get to have more wildcard kinds of searches. Disadvantage, they take a lot of space. Okay, so we got to deal with that and come up with implementation strategies that mitigate that impact. Kind of another thing is there an upper bound to how many distinct words are out there or what the vocabulary can be? Absolutely not. Language keeps increasing. Okay, there are many, many words, and of course we also potentially have to deal with many, many different languages. So really not an upper bound. We know that there's at least 10 to the 37 different words of, length 20 that are out there in that have already been identified and indexed by systems. So it's an incredibly large number. And we also know that the vocabulary is going to continue to keep growing, especially as we move more and more and more to the use of Unicode. And for those that understand what Unicode is, essentially what Unicode offered us is when we went from ASCII, which is the American Standard Code for Information Interchange, which for many years was kind of the standard within computer systems, and for encoding letters and numbers and numerals, right? So the encoding of textual data, we used ASCII for it. And the problem with ASCII was, of course, that it didn't accommodate the special characters in other languages, or there were some languages it didn't accommodate at all. So, for example, Arabic, Chinese, Japanese, Thai, Russian, all of these different languages have their own alphabets and character sets, and ASCII simply couldn't accommodate it. In fact, ASCII, for the most part, couldn't accommodate the special characters that we have even in the Romance languages in Europe, such as German and French and Spanish and Italian. So, they are Czech's another great one where you have a lot of letters that might have umlauts or might have characters with dots on the top of them. All of this stuff couldn't be accommodated in ASCII. So what we wound up doing is going to Unicode. Now, Unicode uses a much bigger structure for those characters, so it actually can encode a lot more characters. But the problem is that where ASCII, basically I could encode every character in 1 byte, right? So 8 bits. What winds up happening with Unicode is that I'm going to have, and depending upon the Unicode version that I'm using, either 2 of those bytes, 8 bits each, or in many cases it's actually 4 of them. Right, so at a minimum, we're 2, and in many cases 4 times as much data to encode the same number of letters to use Unicode. So Unicode is actually dramatically increasing the amount of storage required for our vocabularies. So I just wanted to cover a couple of laws just briefly and tell you kind of why they're important, how we use them. The first one is this idea of heaps law, and heaps is using a power law, and basically the whole purpose behind heaps says that for any collection of tokens. So what does that mean? Well, let's say that I were to go to the web and I wanted to index a website, right? So let's say that I'm going to get 100,000 pages, and out of that 100,000 web pages, I'm going to find 1 million different individual tokens. Remember, we've talked about the fact that when I would have a sentence like the dog is brown, such as this, that a token is every group of letters that is surrounded by white space. So in this particular case, there's a space before and after the word the, so it's going to extract the word the as a token. It's going to find dog as a token. It's going to find the word is as a token. It's going to find the word brown as a token. So out of this particular document, we would extract 4 different tokens. So out of a web page, we're going to do the same thing. Generally, we're going to discard all the formatting information, but all of the textual information within it, the words or the numbers or the terms, we're going to extract all of those as tokens. So basically what Heaps law says is when I know how many tokens are out there in the collection of documents, it's going to be it gives me a way of evaluating how many terms I can expect to have. So for every 1,020,000 tokens, in this particular case, we're going to predict that there is roughly 38,323 terms. Now, this particular study was done against the Reuters corpus, and we've talked about the Reuters corpus. It's mentioned in your book a lot. We use in this class, we're using a subset of the Reuters corpus as this corpus for our own projects. But in the Reuters corpus, there's roughly 1,020,000 tokens, and actually it's more than that. I believe that they're doing the calculation on the basis of the first 1,020,000 tokens. But essentially what they did is a study, and they said, okay, using Heap's law, we want to figure out how many tokens does Heap's law suggest would actually be in Reuters, and it came out with 38,323, and they went back and looked at the same set of documents and discovered there was actually 38,365. So if you're looking at these two numbers, it's kind of a, it's not a big difference between them. It means that the Heap's law is very accurate. And so what Heap's law does is it gives us a very accurate way of assessing how big our dictionaries are going to have to be. That's basically what it's all for. And the reason why it's important is before I go out there and build a system and think I'm going to go, be able to index all of the data within a particular organization, I don't want to get down, halfway through and discover that I didn't build it big enough. I had no clue how big the job was, and therefore, now I'm going to have to start all over again, build a bigger system, get more memory, get more storage. No, I want to be able to know in advance by getting some metrics and determine whether or not I'm going to be able to effectively index and manage all of the documents and information that I have. So Heap's law is one of the tools that gives me an opportunity to do that. The second one is Zipf's law. So basically, Heap's law estimates the vocabulary size. So in other words, based upon some collection of documents and the number of tokens in those documents, it tells me how many terms I'm likely to have in the vocabulary. Zipf's law is a very different thing, right? Because what Zipf's law is doing is it's helping us to understand relative frequencies of those terms. Okay, and basically what Zipf's law says is if I were to take all of the terms out of the collection and I were to look at the very first term, the one that appears most frequently, let's say it was the word the, right? And it appears, let's say, X number of times in all of my document collection. It says the next most frequent word, and let's say that the next most frequent word is A, is going to appear half that many times. And of course the third one is going to appear half again as many times, and so on and so forth. So what Zipf's law does is it gives us a way of understanding how this data is going to look. Again, it helps us to estimate what we're going to need to do from a postings list perspective, because it gives us a way of modeling how the number of terms is actually going to translate in terms of documents and the number of items I'm going to have in my postings list, because of the fact that I have this recognizable relationship. And I'm just going to move on to this document. So I have this recognizable relationship that says each additional term, when I sort them in decreasing order of frequency, once I've figured out the first one, so I know that the word the appears, 1,000 times, then I know that the next most frequent word, perhaps it's as, will be 500, and the next one's going to be 250, and the next one's going to be 125, and so on and so forth. Again, the reason why this is valuable is it helps us to understand and be able to characterize what our posting lists are going to look like, again, from the perspective of being able to size them, determine whether or not they're going to fit in memory, and build our information retrieval system around a realistic assessment of whether or not we're going to be able to fit it into memory and or disk, and what are the things I might need to do to make it efficient because of that.